you can combine everything in a single dynamical equation with the help of stochastic formalism. And since you did yesterday you had a lecture about the stochastic differential equation, so I hope you are a bit familiar with that. That's a bit small still. It looked gigantic from here. Sure, I'll do that. Is it better? That's why one has a long blackboard. You feel it immediately this way. Okay, so if you want to combine everything in a single dynamical equation, that would be the simplest one, not the simplest, I mean, working as a collapse model equation you might think of. It doesn't lead precisely to the GRW model in mathematical sense, but it contains all the physical features of the GRW model, and it was developed by Dioshin. 1989. Of course, I write the simplified version for one particle, then you just put a sum, and you have the many particle equation. This is just for one particle, just to make it simple. And you see that this equation contains basically all the ingredients that you need for a collapse model. You have Schrödinger, evolution. Actually, I don't know if I will I will show you the CSL equation that what PP showed you. If you remember the slides, the structure is the same. It's more complicated because you would like to describe also identical particles, to have a more sophisticated physical theory, and then you need to do something a little bit more complicated. This doesn't work for identical particles, for example, as it is. But I mean, it's good for understanding. So you have the Schrödinger evolution, and then you have the modifications that lead to the collapse. So here, everything is collapse. In the GRW model, this part was an instantaneous jump of the wave function. Now, it is a continuous diffusion process in the Hilbert space that competes with the Schrödinger part. And you see that you have the ingredients of the collapse. You have nonlinearity. The wave function enters nonlinearly. So this is nonlinearity. And actually, as also TP mentioned, these nonlinear terms can be derived starting from a linear evolution equation when you impose a linear but not Hermitian, otherwise it's standard quantum mechanics, evolution equation, and you impose norm of preservation. And then you have stochasticity. Here you have 3. This is the bar like a vector, so 3. We are in 3 dimensions, and so you have 3 independent standard linear processes. And then you have the stochasticity as well. Nonlinearity, stochasticity, and then we will see in a while that nonlinearity and stochasticity are precisely the type combined in such a way to lead to a linear evolution for the density matrix, which is necessary in order to avoid superluminal signaling. It is. And then, so how should you read this? Yes. A standard linear process is the, oh, what's a standard linear process? I don't remember all the definitions. It's basically a white noise. So to be brutal. So it's a white noise, to be precise, is the derivative of a linear process. But basically think of a white noise. Standard, the word standard means that there is no coefficient in front of it. Basically. The correlation is 1 times whatever it is. The coefficient, I put the coefficient outside with lambda. And lambda sets the strength of the linear process. So how should you read this equation? And then we go back. This is Schrödinger, you know. Basically, it takes wave function and makes them spread in space. And also preserves superpositions. This one does the opposite. And so there are two competing effects. Who wins? Well, basically depends on this, on how many particles you have and on the Hamiltonian. As we will see, if you have just a few particles, one particle, this effect is completely negligible, and you just have the Schrödinger evolution. If you have a many particle system, we will see it now, the opposite happens. These effects become dominant, and this loses. So, in the beauty, if you wish, these are models. I don't want to sell them as a theory of nature, but still, I mean, they're beautiful. The beauty of this model is that if you take just a few particles, this is the dominant contribution, quantum mechanics, superposition, interference, uncertainty, whatever it is. If you take only this part, if you take this part of the dynamics for macroscopic object, you have very well localized wave functions, so well localized that they behave for all practical purposes like points. So here you have the, if you wish, the typical delocalized wave function, and here you have a very, for macroscopic object, extremely well localized wave function. So well localized, they behave like points. So classical mechanics of point particles, quantum mechanics of wavy objects. And in particular, the claim, which I will show you also, is that when you apply to this equation to describe measurement situations, you have the entire quantum formalism of operators, measurements, COUAPS, probability, everything counts. So it's in fact, the first GRW paper was entitled Unified Description of Microscopic and Macroscopic Objects. Everything is in one equation with just one coupling constant. It's not that you set things for every physical situation, you change the parameters. That's not a model, that would be a fake. Important that the parameters are set once forever, whether you want to describe the collision of two atoms, whether you want to describe a table or whatever. Okay, so let's go back. I will come back to this. Let's go back to the GRW model. So just to have a quantitative idea, the value, let's spell out the values of the parameters. So this was the original choice of Ghirardi, Riemann, and Weber. I will comment on other choices done. Does it work? Yeah. Done subsequently. So lambda is 10 to the minus 16 Hertz. What does it mean? That for a single particle, a jump occurs once every 10 to the 16 seconds, which is a time span which should be longer than the age of the universe. So basically, a single free electron alone in the entire universe will never see a jump. It's very unlikely that it will see at some point a jump. So it's a very, very rare process. In fact, these models do not want to change quantum nature of matter. Matter is described successfully by quantum mechanics. And RC is a, what is this? This is a typical mesoscopic distance. So even if the jump occurs, the jump produces an effect only if the wave function is much larger than that size. If it's smaller, nothing happens. So these are very rare and mild changes, instantaneous changes of the wave function that leave atoms and molecules as they are. And only when we come to the macroscopic world, we will see that they become relevant. Yep. This is just, we will appreciate better later on. These numbers were just suggested in order that when you want to apply the dynamics, if you apply to microscopic system, this definitely dominates. When we apply to microscopic objects, this will dominate. And this is a choice that suits that. And there are other choices I will show you. Simply, nothing more than that. So there is no stronger argument. It's just a choice. Theoretically or experimentally? Theoretically, no idea. You just have to compare with experiments and see which one is ruled out. No, that will be the end of it. I will show you what the state of the art with the experiment is. Some values have been ruled out, others not. But from the theoretical point of view, I cannot see any argument. I cannot see it. Sorry? RC, remember, it's the spread of the collapsing Gaussian, not of the wave function of the system. The system can have any wave function. It's the localizing Gaussian. Okay, so let's make it now a few pictures just to somehow to understand what that is. So let's consider a single. So we consider at the moment one particle just in one dimension, just to make the thing. And we take a Gaussian just to. So this is our wave function. It's a Gaussian. It's also well spread off in space. The spread is much larger than our parameter RC. And it's localized around the point A in space. Then a jump occurs. A jump occurs, and suppose that occurs exactly in the middle, just to make things simpler. And then, I mean, this is a little calculation that you probably can do in your mind faster than me writing it. So the wave function jumps immediately into the wave function where the localization center is A, and this is, so you have to, just to be pedantic the first time, you have to take your wave function, you have to multiply it by the collapsed Gaussian. You have to multiply your wave function by the collapsing Gaussian. Remember that the localization operator was e to the minus position operator minus center of the collapse. And now we are in the position representation, so the position operator becomes just the position minus the center of the collapse. I will write it again here. Al x for one particle. What was the normalization? I don't remember the normalization constant. Was this one I wrote before. Now we are in one dimension. This is the center of the localization, that is A for us, and this is the position operator, which in the position representation becomes just the position x. Okay, and then you have to normalize. And if you do the calculation, and if you use this approximation, you will find out that this is. Yes. No, we don't know. We assume, suppose it occurs there. Then I will show you what happens if it occurs elsewhere. We don't know where it occurs. It can occur everywhere in space. Stochastically, we just assume it's there for simplicity. Then we will see what happens if it's not there. Okay. So this is the final result. So what happens that after the collapse, so it happens what should happen. The wave function has been localized. Now, what is the probability for the collapse to occur there? I will write it here. P of A, the probability for the collapse to be probability density in A, is equal to the integral from minus infinity plus infinity, according to the formula that I gave you before. That's the probability. So you have to take your initial wave function, you have to multiply it by the localizing Gaussian, and before normalization, you compute the square norm. So the absolute value squared integrated over space. Now you can even compute it here because our psi is Gaussian. It's the initial wave function, this one. And so you can even compute the integral. That's not difficult, but we are not interested here. We're interested not so much in the number, but in the moral. The moral is that you are basically computing the area below here. You are computing. So what does it mean? It means something simple, but at the same time important. So the collapse here has this probability of occurring. What is the probability for the collapse to occur here? So the jump could have happened here instead of here. What is the probability? Morally, I'm not saying mathematically, but morally, is the area below here. And you see that this is much smaller than this. So when the collapse occurs, it is by far more likely that it occurs in this region, which is not exactly, but basically it is the Born rule. Or if you wish, the collapse is more likely to occur where the wave function is more appreciably different. It's morally the Born rule, even though not precise, strictly speaking. Because basically you're not projecting with the rectangle, but with the Gaussian. Okay, so that's how the jump occurs. And of course, if you have a very generic wave function like this, again, the collapse can occur everywhere in space, but the most favorite region will be this one, and then the game is just you multiply this with the collapse Gaussian, and so this is A, and then at the end of the day, you will end up with a state. The jump localizes, and it localizes where the wave function before the collapse was more appreciably. The other case instead, so the other case we do it on the other side. Yes. Why do we use Gaussian basically? Because we want to make calculations. No, for the collapse probability, it has to be the same as the normalization factor. You remember that you send psi into psi xi of x. You do this. This is the collapse. The probability has to be the square of this quantity, because if it's not the square of this quantity, the evolution for the density matrix will not be linear. And you will have superluminous signaling. I will show you that explicitly, but that's the reason. So the choice has to be the square of this one, because otherwise you can't cancel. Okay, suppose that you are in the same situation as before, but now, now you immediately understand. But suppose that now RC is much smaller than R is much smaller than RC. So we have X this is psi So it is the reversed situation. Now the wave function is very localized, but still a jump occurs. And then you might well understand that the Gaussian is this one, before, under the same approximation. So it's not a mathematical result. I use this approximation there. It's the same form as before, but now instead of having RC, we have R because it's the opposite case. So what does it mean? That basically the jump is completely unaffected. The function was localized, and the jump was just a waste of time. It did nothing. The wave function remains local. If you wish, as an assignment, let me just I didn't follow you, sorry. Can you repeat? Yeah, sorry. Yes. It's a random process, one of the two. Either one or the other with equal probabilities. In that case, it's like tossing a coin. Probability of heads and tails is the same. One happens. So it's the same situation. Why? It's just for a matter of simplicity of calculations. Yeah, but it becomes complicated. So all the important point is that it is a localized object. There is no specific reason why it has to be Gaussian, just because it's already difficult as a model. If you make it even more difficult with a complicated shape, we don't go anywhere. But it's just a matter of practical. Okay, so since you asked me about these two, I will just make also this case. Let me see. Okay, this one. Okay, so we consider then the case that you asked the question about. Now suppose that we have this case. So minus A. So we have the superposition. So this is a plus state, superposition of two Gaussian states. Each Gaussian is well localized, but the superposition is delocalized. The distance is much bigger than us. Or to be precise, psi of x is equal to some normalization factor e to the minus x plus a squared over 2r squared plus e to the minus x minus a squared over 2r squared. Just a superposition of two Gaussians and a normalization factor. Now, suppose that a collapse occurs. Nature has to choose. Let's choose a point, whatever we want, this one, just because I made it here the picture. Nature chose to make a jump around position A. It could have made a jump around position A, minus A. And then psi of x goes in psi xl equal A x. I will just give you, which is a new normalization constant, e to the minus x minus a squared over 2rc squared e to the minus x, let me write it better, like this, e to the minus x minus a squared over 2rc squared e to the minus x plus a squared over 2r squared plus e to the minus x minus a squared over 2r squared. It's always the same game after a while. You just have to take the wave function, multiply it by your Gaussian, centered around the localization point, and then renormalize the wave function. And then you can enjoy doing a little bit of algebra with the exponents, and then you will find that under our approximation, so with these two, when you implement these two approximations, this becomes practically equal to 1 over a e to the minus 2a squared over r squared e to the minus x plus a squared over 2r squared plus e to the minus x minus a squared over 2r squared. This is the easy result. And this is basically 0. So this part of the superposition has been vastly suppressed, and so what remains after the jump is A minus A is this one. This one survives, still well localized. And the other one, it's very small, so small that it vanishes basically in the tail. So this is a Gaussian which has very tiny tail. So it's a little bump in the tail of the wave function. But the wave function is localized there. Oh, yeah. Oh, yes, that would be. Okay. Well, we can do that at the end also, or now, whenever. What did they want to say? Yes, that's so. And what is the probability? Well, of course, 1/2. I'm coming. 1/2 for happening around here, and 1/2 for happening around there. So a superposition dies in one of the two alternatives with the usual quantum probabilities. Yes? Yes? Oh, because delta functions are I mean, the delta functions for the collapse? Because, no, that is too much. It's too wild a situation. You would disprove the model experimentally. there would be such a violent collapse to localize a wave function in a mathematically fully precise way in space that the model would become physically disproved. Well, yes. Sorry? Yeah. Well, let me. So to answer the question, let me go to the end of the story. Why? So basically, I mean, but morally, it's because a delta is a Gaussian with RC going to 0. When RC is too small, we will see at the end, experiments disprove the models. You cannot take RC too small. It has to have satisfactory. We will show it. I will show it to you. Then, suppose so we take, again, the superposition of two Gaussians. We take. And the two Gaussians separately are very well localized. But now the superposition is not large, it's small. A collapse, again, so this is minus A, this is plus A, and as before, we assume that the collapse occurs around position A. Now, so psi of x is mathematically the same form as before, the superposition of two. Psi of x, now it's always now a matter of playing the game. And basically, the calculation is almost the same as before, but now the final formula changes slightly because the approximation because the approximations are different. And now this thing here is basically equal to 1, not to 0 anymore. No, the formula, sorry, the formula is the same. No. Let me check, sorry, before, if I wrote it right. Oh, yes, I made a mistake here. This was RC. This was. And so because of this relation here, the exponential is very large, so the exponent is very large, so the exponential is 0. This is RC, not R. So the formula is the same with RC, but now we have the inverse relation. This is basically 0, so the exponential is basically 1. The superposition is there. So it's not that collapse models kill any superposition. Collapse models kill only large superposition. Small ones remain there. Yeah. You mean here? Yes, that will happen. I mean, here, where? Tell me where. I mean, this is half A is here. The probability is basically 0 here. Yeah, there is. So there is a vastly small probability for the jump to occur here, and then the final state would be basically that the Gaussian moves there. Yes. That would happen. In fact, this is something that I wanted to come towards the end. The collapse not only induces a collapse, it also induces a Brownian motion. It makes particles move, make little jumps here and there. That's what happens, yes. It's one of the intrinsic properties. So this would be a rather large jump, which is possible, but basically never you will see. Smaller, I mean, jump in the sense of, not of collapse, in the sense of moving there. smaller displacement are more likely, and actually that's the best way to test this models experimentally. That's what Hendrik does. To look at the particle, whether it moves or not. Okay. So now we come to the important point. One of the important points. So far we have discussed a single particle. Note that for the numbers I gave you here, basically this was a useless discussion because these jumps for a single particle happen once or even less than once in the lifetime of the universe, never. So that's completely useless. But now what happens to a composite system? And then we come to the important part of the story. So let's take a solid object which is exemplified by a diatomic molecule. Theoretician. So that's already too complicated as a solid object. But you will understand the game. So the point is that we have two, not one particle, but two particles, and they are strongly interacting, so they're bound to each other. If one is here, also the other is here. And let's take the superposition so this is the physical picture, so to say. Molecule localized here, plus molecule localized there. And the distance, again, to A is much larger than RC. So if you want to make some sort of picture, of course, this is a cheating plot because this is the wave function is a function of two variables, not one. So this is just a way to make you understand what's going on. We have the two molecules next to the two atoms in the molecules next to each other here, plus the same situation over there. Or if you wish, this state is e to the minus x plus a plus delta squared over 2r squared e to the minus y plus a minus delta squared over 2r squared plus, well, let's write it here, e to the minus x minus a plus delta squared over 2r squared e squared to the minus y minus a minus delta squared over 2r squared. So this is the initial state. Important for the discussion, it is entangled. It's an entangled state. Then we will see, we will appreciate the importance of that. I will never be able to finish. Anyhow, now, the same game as always. Suppose that particle 1 so now we have two particles. Each of them collapses independently. Suppose that at some time there is a collapse. It refers to particle 1, and it's at the right, around position A minus delta. It could have been something else. We take this option. And then psi of x goes into psi xl equal A minus delta psi of xy. So it's xl, not yl, which means that particle 1, which goes with the coordinate x, suffers a localization around position A minus delta. And this thing becomes 1 minus NA, the new normalization constant, more or less, so approximately, because we make the usual approximation of checking who's bigger than who, e to the minus 2 A minus delta squared over RC squared e to the minus x plus A plus delta squared over 2r squared e to the minus y plus A minus delta squared over 2r squared plus e to the minus x minus A plus delta squared over 2r squared e to the minus y minus A minus delta squared over 2r squared. So this is the result that you should get. And now, the same story applies as before. The same story applies as before. This is almost zero. This is because RC is big. Is small, sorry, with respect to the 2A and delta. Delta here is really small quantity. I mean, delta is small. Delta as small as you wish. But what is the situation here? That now this is in front of this, and it kills everything. So it means that after the collapse, the state after the collapse, the state is this one. So what is the important message? That the collapse of one particle, oh, why I killed it? No, I killed the other. This is the left term. This is the left term, and this is the right term. But it's not important, one of the two. That's the important thing. So the important message is that the jump referred only to particle 1. But because of the specific structure of the global wave function, this is not always the case. I will make the counterexample. But because of the specific structure of the global wave function, the collapse on particle 1 caused the collapse of the entire state, also of particle 2. Why? Because they were entangled. They go together. What happens to particle 1 affects also particle 2. I'm coming. So that's the effect. Now, the question is, how often does it happen? We did it for particle 1. We could have well done for particle 2. So how often does this happen? Twice, because we have two particles. We have two possibilities. The rate for each particle separately is lambda. So for the rate for the two particles is 2 lambda. So what does it mean? That when you have your Schrodinger, coming back to the numbers, where are the numbers? Here, to the Schrodinger cat, given these numbers, what is, so a macro object in a superposition, what is the effective, the collapse rate for the single particles? 0. But what is the effective collapse rate for the entire cat in a superposition? It is n lambda, number of particles times lambda, which is 10 to the 24, typically, Avogadro's number, times 10 to the minus 16 seconds to the minus 1, which is equals to, let's see if I can do the math, seconds to the minus 1. So if you want to put your cat in a superposition here plus there, you will not be able to, because in 10 to the minus 8 seconds, that's how much it is, 10 nanoseconds, right? You are good in numbers. In 10 nanoseconds, so before even you start doing the process, a collapse will occur that kills the entire thing. And that's the most important properties of collapse models. That tells you that within the same dynamics, so the dynamics is the same. I didn't change the dynamics. I just changed the system. Instead of considering a microsystem, I consider a macrosystem. If I consider a microsystem, the collapses do nothing. They never happen in life. But if I consider a macrosystem, immediately, as soon as I try to create a macroscopic superposition, there is a jump that kills me and one of the two possibilities. And that's how these models put together the quantum properties of microsystem and the classical properties of macroscopic object. Now, does it always happen for any macroscopic state? No, because now let us consider this other situation, which where you have here, just to understand precisely how things go. Now, instead of considering the case typical of a solid object, that's why I started with the molecule, let's consider the case of a typical of an ideal gas. So we still have two particles, but now the two particles do not see each other. And so the state is so particle 1 was in minus A minus delta, A minus delta, minus A plus delta, A plus delta. With so the conditions are always the same. Very well, not from the picture, but they are very well localized Gaussians, R much smaller than RC, in a superposition which is very much delocalized. The distance 2A and 2A is much larger than RC. So the same situation as before. But now these two particles are not bound together in a solid object. They are separately in a superposition. Or, in mathematical terms, so you see that each Gaussian is exactly as before, separately. But now they are combined differently. Superposition of particle 1, cross superposition of particle 2. It's not an entangled state anymore, it's a product state. And now let's repeat the same game as before. Particle 1 experiences a collapse around position A minus delta, exactly as before. Same thing, but now it's a different state. The collapse goes in the same way. And then this will go in 1 over n A. What is it? E to the minus 2A minus delta squared over RC squared E to the minus x plus A plus delta squared over 2R squared plus E to the minus x minus A plus delta squared over 2R squared cross E to the minus y plus A minus delta squared over 2R squared plus E to the minus y minus A minus delta squared over 2R squared. What happens here? Still, this part is practically zero, this part, which means that it kills this, but that's it. So it means that this part is destroyed and particle 1 has been localized. But nothing happens to particle So here, there is no amplification mechanism. The collapse occurred on particle 1, fine. Nothing happens to the rest of the world, and in particular to particle 2. Yep. As a? Yeah, it's a product state. So this is for particle 1 in a superposition, product for particle 2 in a superposition. Here it's an entangled state. It's particle 1 on the left, particle 2 on the left, plus particle 1 on the right, particle 2 on the right. Here it's particle 1 on the left plus particle 1 on the right, times particle 2 on the left. Why does this describe a bound state? Now I use the usual quantum language. Why is it a bound state? Because if I find in this state particle 1 on the left, then I will also find particle 2 on the left. The two particles are attached to each other. Here, if I find particle 1 on the left, so this is the typical state that is produced by a strong interaction dynamics between the two particles, and then some agent from the outside that creates a superposition object. This state is experimentally realized by particles that don't weakly interacting or not interacting with each other, and the external agent trying to make a superposition. So why do I make this difference? But I make this difference because it's important that the collapse doesn't collapse everything. It depends on the state of the system. And in particular, if you have the Schrödinger cat situation, it does the job. If you don't have the Schrödinger cat situation, it does not do the job. And this is important because these type of physical systems, where you have a large number of particles in truly quantum states, have been realized experimentally, and their quantum properties have been observed. Like in cold atoms. In cold atoms, you have thousands and probably more, or potentially you can have a lot of atoms in the same cloud, and you can do interference with them, and you see interference. So is that a macroscopic superposition? Is that a cat state? Does that falsify collapse models? No. The answer is no for all the three questions. It's not a macroscopic superposition, because a macroscopic superposition is this thing, object here plus object there. This is just a large, this is two, but you just make the game for many. Like in cold atoms, you have a macroscopic system, but still in what I would call a microscopic quantum state, relevant, but it's not macroscopic. It's a microscopic quantum state where each particle independently is in a superposition. Say what? They are not, because, well, not least because the coherence would kill it. If it were entangled, the coherence would kill the superposition before the experiment is performed. So one of the reasons why you can see, interference in such cold atomic systems is that you have a single particle superposition and not an entangled state. Because there is also, because noises would kill it very fast. Do you agree, Andrew? Am I saying something wrong? In fact, experimentally, so let's put it this way. What do you mean? What does it mean? How do you know that they are not entangled? No, you don't go down there and look at it singularly. The theory that explains all experimental data is the theory that tells you that these are of this type. Experimentalists are trying to do this thing now with cold atoms. They didn't do even with two, probably they didn't do. They did two, not even with two, no? You don't know. Because it's difficult, because you have to make them interact. You have to make them, the atoms. And when you make them interact, it's delicate. The Bose-Einstein condensate. Entanglement is what is missing for being a situation of whatever, where is it, of this type, which is the important one for the foundations. Of course, The experiment has its importance. I'm not dismissing it. It's just for the sake of the argument here. There was one of you first, and then, okay. But it's not a superposition of the type here plus there. It's not a known state. I'm sorry? Okay, but is it a known state? Okay, that's what I'm saying. My claim basically amounts to that. It's not a known state. A known state is n here, 0 there, 0 here, and there. They call it known. No, known, so it means, what does it mean here? That if you make the measurement, you find 2 particles here and 0 there, or 0 here and 2 there. So this would be a 2002 state. 2, 0, 2, 0, or 0, 2. If you generalize it to n, it becomes known. So so the meaning of the word is that. So it's a cat state. It's a cat state. That's, for me, it's a known state equal cat state. So since that's not a known state, it's not a cat state. The fact that they are identical then makes it conceptually interesting, out of question. But it's not this thing. There was, no, because just to, okay, yes. I'm sorry? I have problems with the accent, with an Indian accent. I apologize.
So does bound state necessarily always mean position space entanglement?
Yeah, well, yes, because when there is entanglement, so when there is a bound state, so when the 2 particles by interaction they're always close to each other, then unless you break, or you can break the system. But if you don't want to break the system, then anything you do with one particle, you do it also for the other particle. So if you send it through an interferometer, unless, again, you break it, it will be the system goes here plus the system goes there. And so the wave function will be of this type, and it's an entangled state. So given all these premises, yes, it's always an entangled state. Now, the case of identical particle, just because you brought it up, it becomes a little bit more complicated because you have to anti-symmetrize the wave function. So it looks like entanglement, but I don't want to enter into the debate because there is a discussion here whether an anti-symmetric state of identical particles is an entangled state or not. Because some people would say it's entangled because it's not factorized. Some people would say it's not entangled because it doesn't lead to violation of Bell inequalities. This is a debate I don't want to enter into because there will be another school on theoretical physics. Say it again, sorry. Let TPNO worked with that, with the Discord. If you remember, I don't know. I have no idea. I don't even know what Discord is, actually. I know the word, but I don't know what it means. I cannot think, I don't know what a correlation other than entanglement is, actually. So you have to give me an example. Yeah, but I don't know what it is physically. I don't know. So it's my limitation. I simply don't know. I do not know because I never studied it. Okay, then yeah. I will come to that now. It's the thing of measurement. That's what I will come. The probability is 0. The probability that 2 particles, that they have 2 simultaneous jumps, you mean? 2 different particles that simultaneously experience a jump. No, that basically never happens. In this GRW model, the probability of a simultaneous collapse is 0. It's like the probability of for two independent Poissonian events to happen at the same time. But that's different. Here, there is a collapse on particle 1, which affects particle 2, but it's one collapse. The probability of two collapses is basically 0. Can we turn this on meanwhile? No, here, no. Even if you are within RC, it's still the collapse. No, that's CSL, it's different. No, it's a different story. Can we, where is my computer here? I want to show you now, if there are no more questions, I wanted to show you the end of the game. So this is basically, so I will take it from here, I will take it so that I can do. So I wanted just to show you, instead of drawing it on the blackboard, this is probably nicer to see. So this is the situation that emerges from what I told you before. So if you take the Hilbert space, so that's a kind of a idealized picture of the Hilbert space. So the vast majority of states are crazy mathematical states and you don't care about them. But some subset of them represent nice, physically interesting states. So in here, I picture 4 of them. So on the top left, you have the typical state of isolated microscopic system. So a hydrogen atom in the ground state, for example, or a macromolecule that vibrates, whatever. Those systems are stable in the GRW, in the collapse modus or GRW world, because they're small. The collapse rate, even if you sum the contribution of every particle, the collapse rate is still small, because they're microscopic, nothing happens, they're stable. Or on the very opposite side, you have the states that represent classical objects, like a table with a wave function which is already localized. So if you take a table with a localized wave function, because the mass, for the center of mass, because the mass is anyhow big, the Schrodinger evolution will not make it spread forever. For a very long time, it will stay very much localized. This is not a measurement, it's another story. So these are nice states. And again, they're stable because they're already localized. As I showed before, when you have a localized Gaussian, you collapse it, it remains localized. And that's it. Then you have these states I told you about. So you have a more and more complex, a more and more interesting variety of experiments with the quantum system in truly quantum states. And they are complex systems, not just 1, 2, 10, 100, thousands of elements, atoms, electrons, whatever it is, in genuinely quantum states, and you can see interference. This picture, if I remember correctly, was exactly the interference that you see from a cloud of cold atoms, which was separated and then recombined. But also this, so the important thing is that also, of course, stable, I'm not saying fully stable, there are always small deviations, but more or less, these are also stable in the GRW dynamics, because it's not a null state, technically, or a cat state. It's not a superposition thing here, plus thing there, which is the one that collapse models really do not like. Only when we come to this situation of macroscopic superposition, so you have a large number of particles in a large superposition, such that n times lambda becomes large, and also the delocalization distance becomes significantly large, then they are vastly unstable. They immediately die, and they go towards localized state. So that's the picture that, if you have a picture, that should remain of collapse models. So many states are stable. Collapse models affect only macroscopic. And the macroscopic superpositions, and if you wish, the important relevance of the work of Girardi, Riemann, and Weber was to make a consistent model that affected precisely and only this state, not the other ones. Otherwise, you would run into problems with experiments. Yeah. Because of the heating effect, basically, of the heating effect. Yes. They would blur the interference picture. No? Yeah, that's where the bound comes from. And I will talk now. So now I want to talk about experiments and then measurements. Let's see if I can make it in 20 minutes. So this I can kill, this I can kill, this I can kill, can kill. So experiments here. Oh, yes. two condensates, and that's what they did there. But it was not, so it was not the condensate rigidly here, superimposed with the condensate rigidly there. That's the noon state that no one did. What they did, more or less correct me then if I'm wrong, there was the condensate in a single well, then they created a double well so that so to say the condensate moved to the left or plus to the right, but that's not a noon state. And then they released the barrier and they merged, and they saw that interference. But it's not, again, it's just important, that's not known. It's a fantastic experiment, but not for the purposes that we're interested in. Okay, experiment. So collapse models, what do? They do one thing, they kill superposition. So the way to test them is to make superposition and see whether they exist. So you take a system, ideally as big as possible, in a superposition as large as possible, for a time which is as long as possible, and then if you neglect noise, you're a good experimentalist, and you neglect all possible sources of noise, you see these collapse models are wrong, you see this quantum mechanics is wrong. That would be ideally then, of course, experimentally, it's a completely different story, very challenging. And these are, I show you the upper bound. So the situation so far, experimentally. So this is the parameter space. It's for the CSL model, but think of GRW is also much important. It's just technical, the difference between GRW and CSL. The moral is the same. We have the two parameters, RC and lambda we have. And that's a parameter space. So there is this kind of pinkish, red, whatever it is, zone. Exclusion zone, this exclusion zone, it comes from the lower bound. If you take RC, in this case, too large, or lambda too small, the collapse becomes ineffective. It's a weak collapse, to the point that not even the cat is localized. It's too weak. The cat still lives in a superposition, and collapse models lose their meaning. So you can exclude this zone. We took basically this zone comes if you take the smallest object that you see with your naked eye, and you ask for collapse models to collapse it fast enough, then the parameters cannot be here. So this is lower bound. The black spots are, this is a GRW bound, the one which is written there, 10 to the minus 7 meters, 10 to the minus 16 seconds to the minus 1. The other one was a proposal by Adler, basically same value for RC, much stronger value for lambda. And the upper bounds up there come from double slit, basically, interferometric experiments. They are actually, this is interesting because you can see three completely different strategies of making a superposition. So on the top, so that went on Nature, when was it, last year? There was a psychological, or technologically I cannot judge, but psychologically very relevant experiment. They detected superposition of single atoms in a distance of half a meter superposition. So it's really macroscopic, vastly macroscopic distance, atom here plus atom there, not just for the sake of talking, but real. No, really. But the bound is not weak. It's up there. Why it's not weak? Because the system, so the distance is large. The time is also, for experimental time scales, is also big. But the object is very small. It's an atom. It's very small. So, of course, a small collapse could still happen, and that's why you have an exclusion block. But the deviation is very small. The prediction of GRW for this type of experiment, the deviation with respect to quantum mechanics is so tiny that you can neglect it, very weak bound. Or you can take the opposite thing. So one went on Nature, the other one went on Science. So they are balanced. This one, they take a really macroscopic object, actually two diamonds, which you can see with your naked eye, which had a distance of how much? No, it's not there. The distance was of the order of 10 or 1 or 2, 10 centimeters, whatever, but it's a macroscopic distance. So 2 diamonds, not superposition, 2 diamonds. And then with the photons, they created an entanglement of the internal structure. They created. Also there, it is a superposition, because they created a superposition of phonon here or no phonon here. Phonon here means vibration of the internal structure. No phonon means no vibration, which means that you have a superposition of matter here or matter here. So phonon plus no phonon is a superposition in space of matter. What is the benefit? That you have huge number of particles, 10 to the 16, whatever. But you lose in the superposition distance, which is unbelievably small, and in the time scale, because the lifetime of a photon is very small. So you achieve somewhere, you lose somewhere else. And the bound, again, is similar to the other one. Or you can do what Marcus Arndt, following Zeilinger, does in Vienna with molecules. They started with fullerenes, and then they went slowly up with the size of the system. And this is in between, is a moderate mass, or with a moderate distance for a moderate time. And the bound is there. So 3 different strategies, but none of which, so far, achieves the holy grail for testing Schrödinger's cat. Large mass, large distance, delocalization in space, and long enough time. Why? It's very difficult. No, no, basically at that point, since the distance is larger than RC, I mean, so how does the bound there? Here, no, because fix a value of RC. Like here, here it's 1 meter, no? Okay, keep RC here. Then any superposition distance larger than RC, you don't gain anything with any because a superposition distance for the GRW model, but also for CSL, when you reach the superposition distance equal to RC, basically you are at infinity. No, for CSL, no, it's for psychological, they did the half meter to go on nature, of course. But they do it for psychological reasons, come on. No, I'm saying that for testing collapse models, there is no point in going beyond RC. But of course, there is more in life than collapse models. Making a superposition. But the ideal probably is to do what Marcus Arndt does. So you are exactly for luck at RC, and then you have to play with the mass and the time. Better with the mass because it scales quadratically with the so it's better to play with the mass or with the time. The distance is not so much important. Of course, if it's comparable with RC. So Marcus Arndt has it for technical reasons with the grating. It has exactly RC. And then you have to play with the mass. Okay, but there is a different strategy, and now we come, wow, how late we are. We come to, okay, to non-interferometric tests. So some of you asked me, you told me, well, the collapse doesn't always occur on top of the Gaussian. It could occur on the side. What happens if it occurs on the side? The particle moves to the left or to the right. That's a prediction. So the particle, instead of going straight, it undergoes a Brownian motion. Because the collapse is never on top. I did it just for simplicity, but usually it's always on the left, on the right, it's a bit unbalanced. So the particle jiggles around. Now, what happens when the particle jiggles around? If it's neutral, nothing, it just moves around. But if it's charged, yes. No. No, this is not, not Bohm mechanics. This is just the center of the Gaussian. The center of the wave function. I'm just monitoring the motion of the center of the wave function. I should have drawn the whole wave function. Yes. I'll take it the average position. So it's still the wave function. There are no real trajectories here. So if the particle is charged, so actually they're not even particles in the sense of point-like particles. There is only the wave function. So I keep talking about particles, but there is only the wave function. Particle means position in space, point in space. That means particle. If it's not a point, it's a ball. In collapse models, we don't have the point, we don't have the ball. We just have the wave function. So technically, there are no particles, but now it's part of the language. So if the particle is charged, it emits radiation because it's an accelerated motion. So one of the predictions of collapse models is that light comes from everywhere because all particles are charged. Protons, electrons, they're charged. They emit radiation. Of course, they emit radiation at a very low rate, deep in the infrared, so we don't see it. But we could see it if we go in an underground facility and we look, we take a piece of germanium, typically, which is very pure, and experimentalists like it for whatever reason. They like germanium. You go in an underground facility, you put it on the table, and you look at it with the appropriate devices for months, for years, and you wait for light to come. If light doesn't come, at some point, collapse models are wrong. And this is what people do, not for collapse models, of course, but they do it for detecting the dark matter. They take a piece of germanium in the underground facilities and they wait for an event to occur. Event means what? Light that comes out. So they do the job for dark matter. We take the data for our analysis. And I will show it to you now. Or you can do something else. You take, this is what Hendrik does. He likes to play with little balls. So nanoparticles or microparticles. Nano, micro means the diameter, whatever. It's silicon, whatever it is. It's silicon. Glass. Glass, it's glass. So it's a little ball, basically. And you put it in an harmonic trap, and you cool it, in principle, till it's still in space, in principle. Then there is always concern. Collapse models will not let you do that. Collapse models induce a Brownian motion, so it tries to cool it, and collapse models try to shake it. And then how do you see that? You do, of course, not with your naked eye. You shoot the laser, you see the light that comes out, you do some fancy spectroscopy, and what you should see that instead of having a very nice Lorentzian, very well peaked, you have something which is broader, because there is a noise. So there is a shift, but most of all, there is a broadening, and they are good in checking this thing. And so that's, I mean, let me finish, and then but that's what basically you see. You cool the particle, and you see whether the particle stays there or jiggles. It doesn't move much, and you put a bound, which I will show you in the next slide. Yeah. No. The point is that collapse models, at the non-relativistic level, the assumption is that the collapse occurs on the fundamental constituents, which are supposed to be electron, protons, and neutrons. So that's the fundamental constituent. So you should look at that. You might look at the effective collapse on a neutral atom as such. Then you're missing some information. You can do that. And you will have some information, but you will miss some other information. And in particular, you will miss the information about the collapse. Of course, when you have a proton and the electron around, the collapse occurs independently, but then there is also a coherent effect, which kills, at some frequencies, it superimposes destructively. And so it kills the coherence. But there are other regimes where it adds coherence. It's an assumption within the model that you have to take, there are fundamental constituents, and the collapse occurs on them. It's not that the collapse occurs on the table or on the cat. It always occurs on the constituent of the table and the cat, and at the level where at which the models are developed, the constituents are the nucleons and the electrons. And this is now the exclusion plot. For some not nice reason, now the right before has become orange, but it's the same lower bound as before, the exclusion for the parameters which are too big, too small. And now you have the exclusion plot for in non-interferometric tests, so very briefly. This was the exclusion plot, you see? There is a vast white zone, and here there is a much smaller white zone. On the left, that comes from many things, from cold atom experiments, some of them. You take a cloud of cold atoms, you cool it, but the CSL, GRW, shakes it. You do the experiment, it doesn't shake much, the bound. Or you take this germanium in the underground thing, you look for photons to come out, they don't come out, bound. Or you do the little ball thing. Actually, doing the little ball thing is not so easy, and it takes time. But people, since ages, worked on gravitational wave detectors, which is the same story. It's not a little ball, it's a big mirror, but still something that you don't want to move. You cool it there, you don't want to move it because you want to have a very good interferometer to detect small gravitational perturbations. So it has to be still. GRW would shake it. it doesn't shake so much, and you have this exclusion zone. And you see that Adler's value has been excluded. He was wrong, apparently. Now the story is longer, but let's stop here. Sorry? Which is this one? 10 to the minus 11, more or less. To 10 to the minus 16, 5 orders of magnitude, which is much better than a few years ago. So you see this. So first it's nice because now the exclusion zone, it's a finite region. So we know where to look at. Then one could say, then the other nice thing is that these bounds, basically all these bounds came from free. We just analyzed data coming from other type of experiments. So now it becomes interesting to make a dedicated experiment and to go and look there. But why? But it's difficult, and that's also the reason why all the other bounds, they just go around, basically. Because it's difficult to reach the conditions where GRW becomes effective. Large mass, for a long time, well isolated, and so on and so on. Oh, here, no, I don't know if he does, but he has to. I have no idea. He will. Okay. And so that now, so it becomes interesting. So it's not fishing in the open ocean. Now we know where to look. Remember that these models, as I said the first hour, basically are the only way to modify the Schrodinger equation. So it really becomes it becomes important to do these experiments, if not for collapse models, that you might say, who cares, but because this is a test of the fundamental principle of quantum mechanics, which is the superposition principle, which is the building block of our understanding of nature at the microscopic scale. So it's in some sense, it's the most important open question. In some sense. Okay, I want to come to these other, so what happens in other measurements if I measure something else, energy, momentum, spin. So I want to change, okay, we start from here. I will make the story hopefully short. So now, what about observables? What about momentum? What about spin? What about energy? Now we talk about measurements. Now we talk, okay. So we consider several physical situations. We consider an ideal gas situation. We consider a cat type of situation. We consider a single particle situation. Now we consider a measurement situation. So we have a microscopic system, and for simplicity we take just a spin system, a particle. We consider only the spin. We forget the rest of the wave function because this moves in space. We forget just the spin. And we are talking about measurements. So we have a macroscopic object like the LHC in Geneva, a macroscopic object that acts as a detector. And we simplify it with the pointer, with some structure, and the pointer that starts in a ready state and then can move to the left and to the right. And in particular, the interaction, so the interaction is such that if the spin at the end of the measurement, so I'm talking now the standard quantum formalism, then we do in collapse. If the spin, if the outcome, if the pointer moves to the left, then the outcome is spin up. If the pointer moves to the right, the outcome is spin up. But otherwise, we have a fully quantum, I treat everything fully quantum mechanically. So I talk about measurement, I talk about apparatus, but these are improper words. It's just a specific physical system made of one particle, which is coming, and a bunch of bounded particles which behave like what we call a measurement device. So we have the appropriate Hilbert space. So I treat the pointer just like with 1 degree of freedom, the position of space. I neglect the internal structure, otherwise it's too difficult. So basically at the end, I have the spin particle and the movable pointer. The Hilbert space of the spin particle is C2. The Hilbert space of the pointer is L2 over R on the line, just to be pedantic. The dynamics is the von Neumann dynamics, interaction dynamics, which lasts for 1 second and moves the pointer of 1 centimeter. Just to put some numbers, to be very, very clear. Then I have to derive everything from the equation. And this is the Diochy equation applied to our system. You see that there is the free pointer evolution plus the von Neumann interaction. And then there is the collapse for the pointer wave function. The spin state doesn't collapse only in position, so our spin particle never collapses, doesn't see the collapse. The collapse is only in position, so only the pointer has a wave function in position, so the operator is the position operator of the pointer. Of course, and I assume that the spin doesn't evolve in time. Once its initial state, it stays apart from the interaction. So that's the full equation of motion. Free evolution for the pointer with the collapse of the pointer. There is no free Hamiltonian for the spin, whatever it is, and then there is the von Neumann interaction, the one that tells me that if the pointer goes on the left, the spin is up. If it goes on the right, the spin. And then I have to solve the equation with initial conditions. For initial conditions for the pointer, I take the usual Gaussian because it's nice, and there are also other reasons for choosing this Gaussian, but it's not important. Just take a localized pointer in the origin, x0, very well localized point. It's a macroscopic pointer, very well localized. And for the spin, I didn't write the spin state. The spin state, sorry, it must be written somewhere else. The spin state is a generic superposition, plus or minus, up and down. Generic spin state. Now, we solve the equation of motion. The formal solution of the equation of motion, so I'm not talking about measurement, I'm not talking about collapse, I'm not talking about ball codes. Just I'm doing mathematics here. I'm solving the equations of motion. The equation of motion is that one. So formally is a superposition where each term has the form over here. Now, let's look at the Gaussian. The Gaussian, there are two things that are interesting to look at the Gaussian. The distance between the two peaks of the Gaussian, capital X, and the relative 8 between the two Gaussian, which is capital gamma. These are the two quantities which you can easily analyze. This is not, so this is how it's defined. X is the distance between the two centers, and gamma is just the distance between the 8 of the two Gaussian. They can be analyzed mathematically. Now, to make the story short, I want to go to this. The important thing is what happens to gamma. Actually, the beautiful thing is that for this simple but not completely idiotic system, you can prove things with mathematical rigor. And in particular, there are theorems. I just borrowed theorems from book on stochastic processes. You can prove this important thing that with probability 1, gamma, remember the distance, goes either to plus or to minus infinity. With the gamma is the distance. Gamma going to plus infinity means that the Gaussian on the left survives and the Gaussian on the right dies. Gamma going to minus infinity means the opposite. So with probability 1, one of the two Gaussian is incredibly smaller and eventually 0 with respect to the collapse. It is. But when does the collapse occurs? So of course, to go to 0, it takes an infinite amount of time. But the important point is when does it become almost 0. And then this is a first passage time thing, blah, blah, blah. And you can prove that the time for our 1 gram pointer is 10 to the minus 6 seconds. So what is the picture? So the mathematical picture is that mathematically there is a superposition of the pointer going to the left and plus to the right. But in 10 to the minus 6 seconds, one of the two terms is killed. So the superposition doesn't even have the time to form that one of the two terms dies randomly. And then you have what you see in real life. Pointer moving to the left or moving to the right. So at each time, this equation describes what you see. The pointer moving to the left or moving to the right. Give me please some 5 more minutes. With which probability? Now, here it is an important thing. The collapse occurs on the pointer. But the quantum probability comes from the state of the particle. No? The Born rule says that the probability of finding an outcome is given by the square of the modulus for the spin particle. Here, the collapse occurs on the pointer, However, you can prove that the probability for gamma to go to plus infinity is the Born rule, the projection of the initial state on the plus state square modulus, almost, with very great accuracy. And the probability for getting the other outcome. So, in a sense, TP is right. The Born rule is written in collapse. But it is not written in such a straightforward way as it might seem also from what I say. Because I remind you that here the collapse occurs in the pointer, and the Born rule is with the state of the spin system. But the equation tells you that because of the way the collapse occurs on the pointer, and because of the interaction, that the interaction is the one that qualifies the measurement as a measurement. If you take another interaction, you wouldn't have a measurement. This is a measurement because of the von Neumann interaction, this idealized case. So because of the measurement interaction, Hamiltonian, so because of the rest of the dynamics, the collapse, so the Born rule is you recover the Born rule on the spin state. Next, the state after the measurement. Forget about these numbers, there was much talking before. You see, suppose that the wave function collapses to the plus state. At the end of the measurement, the wave function effectively is a factorized wave function where the particle has spin up and the pointer says the particle has a spin up. And also in this case, it is important. The von Neumann collapse refers to the spin state. In our model, the collapse occurs on the pointer. And again, it is because of the interaction dynamics that the collapse that occurs on the pointer effectively can be summarized as a collapse on the spin state. Yes, it's from the bounce, yes, because the interaction Hamiltonian creates a bounce system in some sense. And so you have the equation that I showed you before. It's an equation to describe everything, to describe atoms, to describe tables and chairs and whatever it is. But when you apply it in this way that I showed you very briefly to specific physical situations, then you recover. You have to solve the equations. But at the end of the day, you find a much easier way of expressing results, which is the Born rule and the von Neumann collapse. What about observables and operators? Here, we talk about a degree of freedom which is spin. How does the spin operator come about? It comes about, and the same will be for momentum and energy. Why do we have a spin operator? The spin operator comes exactly in the way that historically came out. No, nothing more than that. At some point, some experimentalists find out an extra degree of freedom, if you remember when you were introduced to spin. So you do not take the classical variable and you put a hat on top, because there is no classical spin there. It was found experimentally as a new degree of freedom. Then, of course, people didn't realize that at the time probably, but what happened is that this new experimental outcome turns out to depend quadratically on the initial state, or more precisely, to be functionally behaving like the diagonal part of the sesquilinear form of the wave function. And Ries's decomposition theorem, you do a little bit of functional analysis, you will find this Ries's decomposition theorem, tells you that when you have a sesquilinear form, you can express it as bracket of a suitable operator. So in quantum mechanics, which is in the situation is the same in Bohr mechanics, so what you learn from collapse model, which is the same lesson that you learn in quantum mechanics, is not that particles are, Bohr mechanics, particles are particles, but apart from that, it's not that particles have a momentum with a quantum particle has a momentum with the hat on top, hat on top, or has an energy with the hat on top, or has a spin with the hat on top. It's not like that. Particles, in Bohr mechanics in particular, but also in collapse models, you can define their momentum, their energy, whatever it is. The quantum momentum, the quantum energy, the quantum spin that people talk about are nothing more than what Bohr had in mind, basically. Bohr had in mind. They are it's a short way of talking about the outcome of measurement. You make a measurement, which we call energy measurement. You get outcomes. And how can you express effectively these outcomes? By using operators. That's the end of the story. So measurements are measurements. In quantum mechanics, you don't know how to describe them. In Bohm mechanics, and I showed you now in collapse models, you can describe them as any other physical situation, just solve the equation. It's a pain to solve the equation each time. You want to have an easy way to give, easy rule to give to experimentalists, otherwise they don't know what to do. And the easy rules is that give them an operator, and they hopefully can make a product and get a number. But apart from the joke, it's nothing more than that. It's just a handy way of dealing with measurements instead of solving complicated equations. But the truth is solve the equation of measurements. Thank you.
Any question?
Sorry? Are there higher order? A Taylor expansion. Yeah, it does look so. I also thought about that. No, at the moment it stops there. At the moment. So. Yeah, you cannot. Yeah, but the white noise is a mathematical idealization. So it looks like a Taylor expansion. The zero order term, quantum mechanics linear. Then you have the first order Taylor expansion, second order Taylor expansion. With the white noise, you have to stop here. Otherwise, the model becomes inconsistent. But white noise, as I said, is a mathematical idealization. The real noise is not white. What happens? No idea. It could be. Just no idea. But it looks like I agree with you.
Also.
Yeah, sorry. Yes, that's the way I look at that. Yes. No. No. So in those that I presented, there is no dissipation. But you can develop collapse models that include also dissipation. So the two things are not, one doesn't necessarily imply the other. There are also decoherence models that are, induce decoherence, but do not have dissipation because of a coarse-grained description. Here is the same. These models contain no dissipation. I believe this is a limitation of these models. You can build more refined models that have dissipation. And if you have dissipation, perhaps the question is what happens to the bounds there? Yeah, that's still open research. That is still open research. We are working on that. It's not easy to answer because it really becomes a matter of being a postdoc.